All right, everyone, we had 2 pages worth of homework to do last night. The first page was 347, number 1 to 12. Any issues with any of those questions 1 to 12 on 347? 8? Yep. 11? I got 8, I got 11. Any more? Going once? Going twice? All right, 8 and 11 it is. Number 8 says, do the oars on a rowboat move with oscillatory motion? Do the rows on an rowboat move with oscillatory motion? Good question. Who thinks they have an answer to that with a reasonable explanation? It doesn't have to be right, just something that seems reasonable. Who thinks that they do move with oscillatory motion? Simple harmonic motion. When I say oscillatory motion, I mean simple harmonic motion, right? One person thinks they do? Okay, who thinks they do not? Wow, that's pathetic. I'm not surprised, but it's pathetic. Tom, why do you think that they do move with oscillatory motion? It's back and forth, and it's repetitive. And I think you'd find that as you stretched, as the oars went back further away from the equilibrium position, which would be the position right beside you, the bigger the force is required to pull it through that water. Okay, motion which the restoring force is proportional to the displacement, and motion that repeats itself. So yeah, I'd say that it's oscillatory motion or simple harmonic motion. All right. Next question was number 11. Says, a red-capped manakin is a bird that can flap its wings faster than a hummingbird at 4,800 beats per minute. 4,800 beats in 1 minute. I think that's like 80 times per second that it's flapping its wings. That's pretty impressive, actually. What's the period of its flapping wings? Well, we know that period is equal to 1 over the frequency. But we need to know the frequency, not in beats per minute, but in beats per second. So 4,800 beats per minute is equal to 4,800 divided by 60 beats per second, which gives us 80 beats per second, or 80 hertz. So the period is 1 over 80, 1 over the frequency in hertz, which is going to give me 0.0125 seconds. So 1.25 times 10 to the minus 2 seconds is the period. That's how long it takes the bird to flap its wings once, to go back and forth once. Okay, basically 12 1/100ths of a second. Sorry, not 12 1/100ths of a second, 12 1,000ths of a second. Okay, so it's pretty quick. Okay, it's pretty quick. Any other issues there with those questions? No? All right. We had another set of questions as well. It was on page 409. Before we do that, let's take a quick look at take a quick look at our waves that we saw yesterday here. What kind of wave do you see? What kind of wave do you see right here? This is like an ocean wave, right? A water wave with maybe a boat or somebody in an air mattress bobbing up and down on that water wave. What kind of wave is that? There's 2 terms, Joe. Yeah, transverse, called a transverse wave. In a transverse wave, waves, remember, carry energy. That's what waves do. That's the whole point of them. They carry energy from one place to the other. And they do it via simple harmonic motion. It's the simple harmonic motion of individual particles within the wave. In a transverse wave, the wave may be going one way, but the particles are bobbing up and down perpendicular to the way the wave is traveling. Versus the other kind of wave, a longitudinal wave, where the waves are moving one way and the particles are vibrating in simple harmonic motion parallel to the way the wave is traveling. So we got our particles bobbing up and down as we have the wave moving to the right. We define a part right here that we call a crest. It's the top of a hill, the crest of a hill, the trough, the bottom, the dip in the hill. The wavelength, lambda, upside down y, Greek letter lambda. We define that as from crest to crest. Where else could we define it? If I start a wavelength right here Tell me when to stop, okay? Tell me when to stop when I reach that wavelength. Tell me when to stop. Tell me when to stop. Tell me when to stop. Oh, you missed it. Do it again. Tell me when to stop when I reach one complete wavelength. You missed it again. Okay, one person didn't miss it this time. Thank you, Dustin. One complete wavelength, guys, is the distance over which the wave repeats itself. It doesn't matter where you start. Okay, we got to go to the spot where it repeats itself, where it begins to repeat itself again. So we could label that as a wavelength. We could label this as the wavelength, right, from bottom of trough to bottom of trough. Doesn't matter, as long as it's the distance over which the wave repeats itself. Finally, the amplitude, the size of the wave, is going to be measured from the top of a crest to the equilibrium, or from the bottom of the trough to the equilibrium. Finally, the amplitude of the wave is related to what? What property of the wave is dependent upon how big the wave is? The energy of the wave. That's a completely logical thing. You don't have to memorize that. Picture a wave. Okay, you're standing on the beach. You guys have all done this probably at some point. Those of you who have been to an ocean at least have for sure done this. You stand on the beach, you're watching the waves come in. You get excited when a big wave comes in. Okay, you let the wave, you kind of go into the water a little bit, you let the wave chase you back in. Okay, you know intuitively when a big wave comes that it's the most likely one to knock you over. Why is it the most likely one to knock you over? Because it's the one that carries the most energy, right? The big waves carry energy. The amplitude of the wave is related to the energy of the wave. What kind of wave is this again? Not transverse, but give you a hint, it's a long wave. It's a longitudinal or a longitudinal wave, yeah. And a longitudinal wave is like a sound wave, right? Where we're not going up and down like this, but rather we're going an area where we have kind of an extension of the medium and then a compression of the medium, and then an extension, and then a compression, and so on. These areas where we have high density, where the slinky in the demonstration yesterday was squished together, or the air molecules, when we're talking about sound waves, we call them compressions. Those areas where it's stretched in between the compressions are what we call rarefaction. Now, if the wave is going this way, if the wave is going to the right, the particles are moving in simple harmonic motion, but they're not moving in simple harmonic motion like this, like they were in the other kind of wave. Rather, they're moving back and forth parallel to the direction of motion of the wave. So in both cases, okay, whether we get transverse or longitudinal, it's simple harmonic motion. That's what it really is. But it's simple harmonic motion of individual particles that is perpendicular to the way the wave moves and is parallel to the way the wave moves. Yesterday, we also identified two equations that are valid when we're talking about wave speed, trying to do a calculation. The first one, V is equal to delta D over delta T. Nothing new there. First day of class in Physics 20, we looked at that equation, V equals D over T. We learned that it's valid whenever we have a constant speed. Well, waves travel at a constant speed, so this equation is valid. Now, we also said that the distance over which the wave repeats itself is the wavelength. The time over which the wave repeats itself is period. But we know that the period is 1 over f. If we simplify this a little bit, V becomes equal to f times lambda. So both of these are on your data sheet, albeit in different places. Be prepared to use both of them in the analysis of waves. Now, your second set of homework last night relied on these two equations on page 409. Let's take a look at those questions now. Any issues with 1 to 3 on page 409? 3? Any others? 2? All right, let's look at number 2. Because the submarine sonar system sends a burst of sound with a frequency of 325 hertz. The sound wave bounces off an underwater rock and returns to the submarine in 8.5 seconds. The wavelength of the sound is 4.71. How far away is the rock? Let's go 4.71 for the wavelength. Let's go a time of 8.50 seconds. What are we looking for here? Oh, sorry, we have a frequency as well, right? What are we looking for here? How far away is the rock? We're looking for delta D, right? What do you want to do here, guys? What do you want to do here? Kind of a tough question, eh? We're going to solve for distance, but we don't know what speed is. But we know what the wavelength is and the frequency is. Let's get the speed. We know that V is equal to F times lambda. 325 hertz times 4.71 meters. What do we get there? What's the answer, James? 1,530 point. Thank you, James. You know what I appreciate most about that is how quick you were with your response there. So that's our speed. Now we want to find the distance. The easiest way to do that now is to say distance over time, right? Rearrange that. Take the time up by multiplying. So we get 1530.75. Ready for this? 1530.75 times a time of 8.50 seconds. What do you get there, James? 13,019 point. Thank you. Does anybody else agree with that? No? Okay, so it is right. It is right. 13,019.02 meters. The only problem is when you look at our answers here, it's not what it says. It says 6.51 kilometers. Well, first of all, if we convert this to kilometers, we're getting a lot closer, right? 13 kilometers. But wait a second, the answer is 6.5 kilometers, half of that. Why? What have we done wrong here? Well, we haven't really done anything wrong, but what have we not done yet? Yeah. Okay, so when the sound bounces off the rock, okay, this is the path of the sound, right? Here's where it starts. Here's the rock face. It bounces off, and then it comes back. We just found the distance of the sound there and back, because the time that it took to go there and back is the time that we used, 8.5 centimeters. We don't want the distance there and back. We want the distance there. So what are we going to do with this? Divide it by 2. Okay, you got the return distance, and sometimes you might want that. That's not what we want here. Let's divide that by 2. We're going to get 6.51 times 10 to the 3 meters, or 6.51 kilometers. Okay, how many people did this question and got 13? Okay. And then you looked at the answers and said, wait a sec, 6.5. Did you recognize at least when you saw the answer was 6.5 why it was half of what you got? Okay, fair enough. Number 3, here's a good question. This is similar, I believe, to the last question on the West Ed alternate assignment. I believe it's similar to question number 9 on the alternate assignment. It says a fisherman anchors his dinghy in a lake 250 meters from the shore. The dinghy rises and falls 8 times per minute. He finds that it takes the wave 3 minutes to reach the shore. How far apart are the 2 wave crests? So kind of worded kind of crazy, but in the end, no harder to solve than the question above, as long as we recognize what we're given here. This 250 meters is not the wavelength. That's how far the wave travels. How long is the wave? I don't know. That's how far the wave travels, from the dinghy to the shore. It rises and falls 8 times per minute, so the frequency would be 8.0 cycles per minute. We want cycles per second. We'll deal with that in a moment. It takes 3 minutes to reach the shore. That's going to be 180 seconds. We want to know how far apart the wave crests are. What are we looking for here? We got the distance. We want all right. After that brief interlude, what are we going to do to find the wavelength here? Well, we only have one equation with wavelength in it, right? V is equal to F times lambda. So let's use that one. But we don't know the speed. So got to get the speed how? Distance over time, good. 250 meters divided by a time of 3 minutes is 180 seconds. What's that going to give me here? 250 divided by 18. 1.888 repeating meters per second. All right. So we're going to say 1.888 meters per second repeating there. Meters per second. Oh, sorry. What did I say? 1.388. Yeah. Divided by the frequency here, which is 8 cycles per minute. How many cycles per second would that be? Because that's what we want here, right? Cycles per second. 8 cycles per minute. 8 divided by 60 would be the same as 4 over 30, which is 0.133 hertz cycles per second, right? Now we do the division there, and when we do 1.388 divided by 0.133, works out to be to 2 digits. We can see here it's 10 meters, right? Good? Are we good there? These are good questions, actually. 2 and 3, these are 2 good questions to have gone over here. Not crazy hard, not impossible questions by any means, but challenging enough, okay? Expect to see something like that on a unit test, okay? I think those are good questions. Not too easy, not too hard. Okay, good balance. All right, let's take a look at check and reflect questions on page 410. I'm going to have you do these questions as homework tonight. We'll give you about, let's see, we'll give you about 4 to 5 minutes to work on those right now. Page 410, number 1 to 10. All right, we just did a couple of demonstrations with the slinky, and we saw what happens when a wave encounters a boundary between 2 media, between 2 different materials. There are 2 things that can happen when a wave encounters the boundary between 2 materials. One is reflection. The other is transmission. Reflection means it bounces back. Transmission means it keeps going. We always get some of both. If the 2 media, medium 1 and medium 2, material 1 and material 2, are very, very similar to each other, like in the first demonstration we did with the 2 different slinkies, then most of the wave will be transmitted. Most of the wave will keep going, but a little bit will be reflected. If the 2 materials are very different, like the slinky and the person, right, it's going from slinky to person, then a little bit will be transmitted, but most of it will be reflected. So you're always going to get some of both. The closer the materials are to being the same, more of it is going to be transmitted. The further apart the materials are, the more different the materials are, the more reflection you get. Now, let's take a look at the reflected portion of the wave versus the transmitted portion of the wave. The part of the wave that gets sent back, that bounces back. It can be reflected in one of 2 ways. It can be reflected right side up, upright, or it can be reflected upside down, inverted. If it's reflected upright, it's because the wave was going from more dense to less dense medium. In other words, it was going from a medium that was not fixed, okay, or a freely moving end. In our demonstration out in the atrium there, you saw that the slinky that was not attached to anything at the bottom, when the wave went down on the library side, it came back on the library side. It comes back inverted when you're going from less dense medium to more dense medium. When somebody was holding on to the other end of the slinky wave was going from slinky to person. The person is physically more dense than the slinky is. That wave is going to be reflected just the same as it was in the first case, but it's going to be reflected upside down. so on the opposite side. As Javi was holding on to the end of that slinky, when the wave went down on the library side, it came up on the other side because it was going from less dense to more dense. That was a fixed end, where the end of the slinky was attached to something solid. Now, we can't demonstrate this with a slinky, but at some level, you already know this. What if the wave encounters the boundary at an angle? What if it encounters the boundary at an angle? We want to look at the part of the wave that's reflected. Some of it will be transmitted. Some of it will keep going. But the part of it that's reflected, how's it going to reflect? Now, here's the initial wave. You guys know this, right? Because if you've ever played pool, you've bounced a ball off of the bumper knowing that it would come off at the same angle that it struck the bumper at. We're going to measure what we call a normal line here. I'll put in a normal line here. The angle of incidence, we're going to call it. We'll call this the angle of reflection. The law of reflection says that the angle of incidence is equal to the angle of reflection. In other words, if you hit a pool ball off the bumper at an angle of 37 degrees, which way is it going to bounce off at? 37 degrees. The angle of incidence is measured from the normal line, will always be the same as the angle of reflection. Now, that reflected wave will be either right side up or upside down, depending upon whether it's going from less dense to more dense or more dense to less dense. But what we want to identify here is not so much right side up or upside down, but rather, where does it go? Well, it goes off at the same angle that it struck it at. The angle of incidence equals the angle of reflection.